Uh, so first of all, I'd like to really thank Lionel and Stefan for having me here, and also thank Stefan for helping me with BayesiaLab over the years, and Bayesian Networks in general, and giving me feedback. Unfortunately, I had to shift over to a Python environment because I needed like lower level access to communicate and customize some user interfaces for people in my field, to communicate Bayesian networks to people in my field. But I still actively use BayesiaLab as a prototyping machine for prototyping my Bayesian networks and even validating my Bayesian networks. So I'm not sure if that qualifies as abusing or not. Yeah, so as Stefan said, I'm a PhD candidate in architecture at the Singapore University of Technology and Design. So I come from the field of architecture, and architecture being buildings, not all the software stuff. Yeah, so the motivation here, I'll give a quick overview of what I'm going to be talking about. So I'll explain the motivation, explain how, forgot to mention, so I'm going to share with you my application of Bayesian networks in with engineering simulation in the context of building design. So I'll explain briefly how engineering simulation is used, or how it's important in building design. I'll explain also how simulation is being used by architects, not necessarily engineers, as part of conceptual design. Also explain how my approach of simulation metamodeling to certain challenges, and then eventually how I adopt Bayesian networks as a metamodel for simulation, and finally conclude. So the motivation here is to help architects and engineers make meaningful inferences from engineering simulation using Bayesian networks. So quick background, for decades, engineering simulation is used actively by engineers, traditionally by engineers, to help understand how a design that was passed on to them by architects is going to behave, and then eventually feedback information on how to fine-tune it or whether to scrap it completely. And there are various types of engineering simulation, for example, understanding how wind affects the tower structure, how the solar gain, how the geometry affects the solar gain of the building, even understanding acoustics in certain geometries, and so on. So the list is endless. But it is extremely important if we want to push boundaries of design. And in fact, simulation is helping reaching new heights in design, quite literally. For example, in the case of the world's tallest tower, it was important to understand how the building reacts to lateral loading due to earthquakes. And eventually, this information helped them understand where to place where to place the foundations, the pile foundations, and also understanding how the dimensions of these foundations and how deep they should be. So this was all really important information they needed to understand beforehand, before construction, in order to feed back to the architects on how to fine-tune their design. So more recently, engineering simulation is now also being used by architects in the early stages of design, and it's actually become widely available. So there has been a shift in architecture where we can no longer design static geometry or design static forms, but we actually design systems. So there's been a computational shift. Architects are now in school, even in education, are learning how to write code and how to design their own software tools, where we kind of design algorithms to generate forms. So this is just an example of a roof structure. So where we now select parameters, design parameters, and gives us a much larger variety of geometries that we can explore, which is what we call the design space. So the design space here is bound by these parameters we selected. And generally, these parameters are geometric, material related, so it depends on the particular problem. So now with the availability of faster simulation, so faster numerical methods, and also with this computation framework, we can even couple engineering simulation with this sort of design exploration, so we can get quick feedback on our designs. And this is quite insightful when you're in the early stages. So this actually helps also the relationship with the engineers. So when we're designing forms as architects, we're designing forms that have engineering intent, which means when we feed back to the engineer, eventually we're saving a lot of time as well, because the geometry or the building we're designing actually makes sense from an engineering perspective. So it's feasible, or at least within feasible range. Within this framework, you can also plug in some stochastic optimization to have some iterative search for forms that perform, that have, let's say, certain properties. In this case, it's searching for properties that have, for geometry that have a low deflection. Deflection being how much the roof structure is bending, which is important information, of course. So you can search space iteratively and generate these forms. However, the challenge here is that when we deal with multiple variables, design variables, so here in architecture we tend to call them design parameters. They are variables. So when we deal with many design parameters, which is normally the case in architecture, it becomes a challenge to understand. The system becomes a black box, and it becomes hard to understand the relationships between the design parameters and the response that we're getting. So it becomes hard to navigate this design space. Eventually, we resort to kind of these stochastic tools like optimization, which is in itself a black box. So there is no understanding of why we are getting this result. Even in the case of optimization, why is this the best result? Why, in terms of the inputs, in terms of the design parameters, why is this the best result? So my approach is a statistical one, as you might have guessed, and the idea is to introduce simulation metamodels. So a metamodel is just a statistical approximation between the inputs and the outputs, and that is used as a replacement of the actual simulation software. So in the case of computationally expensive simulation in engineering, this is used heavily as a quick means to improve your design analysis cycles. So it's used in various fields, such as automotive engineering, in this case crash simulation, which can be computationally really demanding. In facade engineering, understanding how glass, in this case, understanding how glass would react in terms of its stresses when introduced to wind. And again, this is really computationally demanding, so they introduce, in this particular example, they use neural networks as a meta model. Even in aerospace engineering, from a non-simulation perspective, they use meta models for quick onboard computing on drones. Let's say if there's wing damage, and it uses meta models to compute quick analysis and to re-update the path flight based on the amount of wing damage it's got. So a typical metamodel is constructed by setting a parameter space, sampling that parameter space, of which we assume we have no prior information on. So we use certain algorithms such as quasi-random sampling or Latin hypercube sampling from Fisher to sample literally everywhere, but in a sort of quasi-random way, so that you do not induce systematic correlation. So the idea is you sample everywhere because you know nothing about the space. And then evaluate those data points, in this case using engineering simulation, and fit some form of model within those points. So this would be our meta model, right? Now there are most traditionally in engineering practices, because in architecture it's not done so much, typically you use methods such as polynomial regression, kriging, splines, and even neural networks. However, the challenge is that, so once you have this model, of course, you can then perform analysis quite quickly. But the issue is that it is still hard to access the function. So you're limited again to sort of trial and error, or stochastic search. So because when the number of variables are many, the function is still inaccessible to question why the inputs are affecting the outputs. So the solution in terms of the knowledge extraction is not solved. So this is where we take a non-parametric approach, where instead of compressing the data points into functional relationships, this is my very conceptual illustration of a joint probability distribution, as I had to explain to architects and designers what it is. So over time, I have to develop some form of story. So instead of compressing the relationships into functional relationships, so the data points into functional relationships, we consider all the data points that we've sampled in the space. And so as a joint probability between the inputs and the outputs, so between the design parameters and between the simulation response from data. And we use Bayesian networks for this. So the network itself is quite simple. The topology of it is quite simple. It's just inputs mapped onto the outputs, and so the design parameters are introduced as random variables, as nodes into the network, and the distributions, the priors, are simply frequency distributions from the data. So it's not a causal model, it's just an observed model from data. And again, so actually generally these distributions that I'm showing here should be somewhat uniformish, because when we use the sampling algorithm, pseudo-uniform sampling algorithm, it generally looks uniformish. And the idea here is that as opposed to functional models, typical metamodels that are limited to forward operations, with Bayesian networks, there's no direction, right? So we take full advantage of the idea that you can, of this bidirectionality, which is extremely helpful, and I will show how in a case study. So Bayesian inference here helps us slice what I like to illustrate as sliced the joint probability distribution to reveal the dependencies of certain queries we make. In this case, forward, which is simply prediction of the response, of the simulation response, but more powerful is the reverse, which is predicting the posterior. So understanding which inputs will give me a certain output, and in the case of engineering simulation, which geometries, which building shapes, which structural shapes will give me a certain deflection of a range that I'm interested in, which is extremely powerful. Again, I will show this in the case study. So here I will show a simple case study, and the inspiration is taken from this old structure, which is quite famous, like in the architecture community. It's a stadium roof structure, and it's designed by a structural engineer / architect, Pierre-Louis Ginervi, who's now gone, who's now dead, but he was great in his era. So here again we build this so-called parametric model. So we select our parameters, we build this parametric model of the geometry. So we then plug in the analysis, and once we have this framework, so as you can, one point is, as you can see, I mean, if I go back a step, it's still, let's say we know nothing about the behavior of or have limited understanding in solid mechanics, as an architect, as a designer in the early stages, it's difficult for me to make inferences about which geometries are going to behave in a feasible manner. So, and this is simply an issue of the number of parameters we introduce. So, and the number of parameters, normally we want to have a lot of parameters because we want to have a lot of control, and also we want to have many more options in the design space. So, okay, so we have the setup, and what we do is we use a sampling algorithm to sample the inputs and generate data. So the data is basically your input vectors, which are your sampled inputs, and the resulting response from each iteration. So for this particular example, we used around 4,000 data points. So we have full control over the data, over how many data points we want. Although one limitation is that when the simulation is expensive, then it kind of contradicts the scope of building a model. But the justification is the knowledge extracted is insightful. Later on, I will discuss some quick approaches to reducing the dimensions, perhaps, of the problem to require less data. So the format that you will mostly recognize is this. So this is the Bayesian network would look like this. So the inputs are the red nodes, and the output, the target in this case is the blue node. So the directions are, for illustrative purposes, again, it's not a causal model. So because having too many nodes having too many edges in a node can give you a massive condition probability table, I reverse the nodes, which does not affect the results or the posterior distributions, but it's just simply a hack to avoid having a massive table. Again, because this is not a causal model, it does not matter. So to give you a little insight, again, to communicate Bayesian networks to designers and architects, I had to leave BayesiaLab and implement some form of user interface that designers can play around with. So to give you insight, to give you a context, this is the software sort of kind of like environment we work in. This is kind of like a 3D modeling software, and on the right-hand side you have this plugin called Grasshopper. There are various approaches to using this, but there are various alternatives, but this is the most famous one, where we design these sort of plug algorithms and assign these sliders to kind of control form, generate different geometries. It's quite powerful, and this little plugin has all these new connections to simulation software, so you can really plug in everything into one model, and at the same time visually illustrate the results on the left-hand side. So what I did was I tried to introduce Bayesian networks into this environment. So using the same language of sliders and these kind of like spaghetti, I developed these kind of like histograms above the sliders. So the idea here, with regards to our problem, is let's activate this. So this is the marginal state, right? So they look somewhat uniform because of the sampling algorithm, the inputs. And on the right-hand side is our output, is the deflection of the structure from the data. It's just a frequency. Again, so we can perform bi-directional inference. So let's say we want to predict the deflection of a certain structure that has these particular input values, and the mean of the distribution actually matches the actual value, in the simulation. Now, what's more interesting to us is the reverse. So the designer can simply say, I'm interested in structures that have a deflection of a certain range. In this case, I'm not sure if it's visible, but it's like 40.13 millimeters. So the posteriors are updated, and it gives a quick insight. So again, when we deal with architects and designers as well, we talk a lot about, we try to make things intuitive and sort of visual. So here, on a first glance, you can tell where to search in the design space, where are the feasible regions in my design space to give me certain structural shapes that are efficient, that are going to give me a deflection that I've queried. So, for example, here, what I'm doing is, the designer can literally just search in the bins with highest probability, basically you reduce the vague design space into a smaller design space that's more meaningful to my query. So all geometries that are found within the highest bins are all engineeringly feasible. Sorry. So one other thing is that a second piece of information that you extract is the sensitivity of each parameter. So when you compare to the marginal state, the change in distribution tells you also how sensitive that parameter is to that particular query of the output. So if you can tell, the second, third, fourth, and fifth distributions are not as sensitive as the first and the fourth. So from a solid mechanics point of view, that actually makes sense. So in fact, here, that is the depth of the beam, the bottom one, sorry. So when you increase the depth of the beam, which is the height, it actually makes more sense. It actually makes a more efficient structure, which is a known fact. It's just a simple example. So again, so if we reduced that space, and here I just randomly generated the designs within those ranges only, so within the meaningful ranges, the bins with the highest probabilities, and they all fall below the queried deflection, which is 40 millimeters. So also, the cool thing about Bayesian networks is that you can also have multiple outputs. So we can explore trade-offs between objectives. In this case, I'm talking about the weight of the structure and also the deflection of the structure, so the amount of bending of the structure. And we can query both of them, and that's actually really powerful because now we can find spaces in the design space, regions in the design space that will actually satisfy both queries, which is doable in, let's say, multi-objective optimization, so using some form of stochastic optimization. But again, it will simply give you one result or a range of results, but not giving you more insight into why this is happening. Again, the change in distributions here gives you a little more insight. It gets a little more complex, but you get a little more insight into how these particular parameters are going to affect the deflection. So one thing, when I skipped over to Python, One thing I try to do is overlay the, this is my like very basic visualization of the distributions, is overlay the priors and the posteriors to get an insight into how it's changed. And that gives you a quick intuitive understanding of how important those parameters are to satisfying that particular query. And the same for the multiple outputs. So some limitations and some problems that maybe you guys are probably more experts than I am in, and that I've seen also as a common limitation amongst us, is the discretization of the variables. So in my field, the discretization not only has to make sense in terms of the model, but it actually needs to make sense for the designer. So like, if we want to set inference, set evidence on certain bins, the bins need to make sense in terms of their ranges. They need to make sense for the designer's queries. So how do you find the trade-off between finding the meaningful bins, but also the discretization that makes sense for the models, such that this model is not sensitive to that? So in fact, so one problem using equal binning has been with, if the distribution is if the frequency of my sample data, of the response data is shifting to the left, let's say, and I use equal binning, of course it's always going to guess correct because all the data is lying in the first bin. So any outliers are misguiding the discretization, and this can totally misguide your accuracy prediction. So I've explored other methods like percentile binning, which has worked slightly better, and also recently I've looked at minimum description length for discretization. It's used in other fields. Also, the amount of data required, as I mentioned earlier, is a bit of a problem, and it's a bit of a contradiction. So if the engineering simulation is computationally demanding, then it's going to take days, if not, in certain situations like automotive industry, it could take months to generate so much data, depending on the number of design parameters you're considering. So one way of kind of like counterfeiting this is by reducing the dimensions using methods like sensitivity analysis. Recently explored a few methods that use smart design of experiments to not require too many analysis results, to be able to reduce the dimensions. So that's one way of going about it. But the ultimate justification is that the knowledge that is inferred from this approach is more valuable in a way than the computational expense. That might be maybe a cheating. Also, an issue is the number of edges going into the node. So if you have too many inputs and too many outputs in your metamodel, you introduce your conditional probability table is huge, and this is quite a problem. And I don't think there's a workaround this. So as a sort of concluding comment, the idea of using a non-parametric approach and using inference to take advantage of sort of this bidirectionality helps us go from a vague design space. So as a designer, when I set up the system, I know nothing a priori, or assume I know nothing. Going from that to regions in the design space that makes sense to me. So literally, engineers can run the simulations. They can build this sort of meta model. They can then hand it over to the architects with this sort of reduced range in the safe zone, and the architects can still explore different geometries, different variety of materials, and so on. But they're sort of working within the safe region, within this engineering feasible region, and that is very helpful because it improves the communication between the engineers and the architects. Also, this is my BayesiaLab slide, by the way. Finally, so the great thing I think is that you can get meaningful insight over so many dimensions. In this case, if you have many inputs, which is, again, like I'll repeat again, is really hard to do with the traditional approach that we use, just using stochastic optimization or just trying to find designs by trial and error. So it's extremely powerful. In this particular example here, it's an example from another type of simulation involving heating and cooling of a building that I was helping a colleague with, and and immediately, so they ran like, I don't know, they were doing all these complicated sensitivity analysis methods, but immediately I could tell when I just plugged in the data and queried, let's say, the lowest of the outputs, because they were trying to minimize the outputs, I could immediately know where to search in the design space to give us those building designs that will satisfy those criteria. So from an optimization point of view, it's quite powerful, I think, in a design sense, of course. So finally, I'd like to thank again Bayesian for having me here, and also for the introductory courses that were really, really helpful in Singapore, and Stefan particularly, who I've annoyed a couple of times. So that's it.